Hi everyone, welcome to another episode of the Common Lisp Study Group. I'm your host Ron Batum with Atlanta Functional Programming. Today we're going to continue our implementation of some extension functions that are requested as part of the Chapter 7 exercises on the student word problem solver that we've been exploring and been looking into the last couple of weeks. Last time we were trying to see how the student program could be extended to specifically implement things that could handle special characters. And it looked like originally um, some misunderstanding was occurring on my part where um, when I read the question, make sure you handle special characters properly in the book, I didn't quite understand that they meant that right now special characters aren't actually fully implemented. In some cases, what's happening is they are being retrieved and parsed into the actual symbol that's being created, and that's in the case of like say when you're dealing with floating point numbers. But in the case of like say commas and things, what's happening is we're ignoring them altogether because of the fact that the commas are actually ending up being used as say a line separator to actually complete a parse of a particular equation. So um, you would see that in the example that we were working on the on last Saturday. If you recall, we had a problem like the following simple problem. Uh, Sorry, one second. Uh, Seem to have lost my control key. Okay. Okay. So if we go here and we actually go and look at something like say problem number two, which is the simple problem. If this is a simple problem that I originally created for us when we were actually looking at the student program originally. And you can see that the commas here are kind of indicating that there are separate equations representing Alice is twice Bob's age and Bob is twice Dave's age, right? So if we end up going ahead and, uh, sorry, if we uh, go here and go ahead and load this into here and we just go run say student on simple, you could see that what ends up happening is it will create the following equations: um, 2 times Bob, 3 times Dave, and that's indicated by the fact that the line separator, the commas operator that is in the case of Common Lisp represents things that are unquoted inside of a backquote when you are dealing with macros. In this case, the student solver is just ignoring them and indicating them as being kind of like the equivalent of a new line or a period to indicate the completion of a sentence. However, in the case of, say, the equation here, where we have, um, say, a uh, a word problem that contains like a floating point number, like in the case of the price of radio is 69.70, and this is directly from the book Exercise 7.6, Part A. And if the price is 15% less than the marked price, finding the marked price ends up being created as the following. Um, we first um, go ahead and put this in, and if we go and then REPL this, if you recall, this will end up creating something that looks like it has a constant value, but what's happening behind the scenes is and I can show this to you as well. Um, Dang it. There we go. You end up getting something that shows you the equations being marked off. We see that the constant is there, the 69.70, but what actually is happening is and we could see this when we run translate equations to expressions, we get the following list of actual parsed equations before we actually generate um, our we actually run it through the solver using solve. Okay. And the main key thing here to look at is that pipe 6970, because what that is actually is a symbol. For those of you who are just joining us who haven't been following along our common list study groups, I encourage you to go look at our earlier videos on some of this stuff when we talked about symbols. But in a nutshell, when you run make symbol with a name that has special characters, or even creating a user-defined symbol like saying my name, like so, which has like a dash. What ends up happening is it creates an uninterned symbol with pipes in uh, Common Lisp, and that 6970 is a actual symbol object that contains the string has a name $69.70. So we need to go in and actually adjust the parser of the of Common Lisp to actually deal with this specifically. Um, so let's go in and actually take a look at a couple of things, a couple of experiments, and kind of review how floating point numbers are actually represented in Common Lisp. So to start with, if you just type in a floating point number, like say $69.70 here, and you don't have autocomplete constantly barking up your thing, you end up actually seeing that Common Lisp does support floating point numbers directly, right? So float, if you take a float p here and you say $69.70 here, you could see this will actually return a true as expected. Additionally, we have a converter. So if you do a float p and then you do a float of say 5, this will actually return an appropriate floating operations. And we can actually see this when we type in an integer here and we do float and pass in a float object. Now, that float cast, if you will, okay, and it is not really a cast. It's actually constructing a float object. So if you do an EQ of here and you say float 5 and then 5, and these should be not EQ because of the fact that they're two different objects, although internally they hold the same value. Additionally, they shouldn't be actually EQL, if I'm not mistaken, because it doesn't do internal conversions. It may. Actually, I think these are not EQ, but they are EQL and equal. Okay, so they're not EQL, but they are equal, right? Oh, yeah. Okay, so they are actually doing the correct thing. So all three of these EQ, EQL, and equal are expecting them to be the same object, or the same value with the same type. So although 5.0 is the same as 5, technically because they are two different types, the actual underlying override doesn't do an internal implicit cast on the 5, so you end up getting nil as expected. So if you ended up doing 5, say, so if we do this being float 5, like so, this will be true because of the fact that they will end up mapping into the same object. We'll actually recognize that they are technically the same object internally, and we'll look at the underlying values. But um, that's only because of the fact that the parser internally, if I'm remembering this correctly, and folks who are more familiar with the internals of how, say, SBCL and some of these common list works, please feel free to correct me if I'm wrong. What it does is it will actually take that expression, evaluate it, and then internally share the object, unless there is code that it recognizes in the form, that what's it? It recognizes that there's code that's modifying that particular value at some other point in some different expression. So only at that point will then create a copy of it. So then you end up having this implicit sharing for the lifetime of the expression until the point of which one of the two copies, if you will, or one of the two references have to change. And at that point, Common Lisp makes the conservative decision of making a copy object in memory, have that get the one being modified, and the original stays the same, so that the rest of the code can actually go in and use that older value as expected. In the case of the parser here, though, we need to actually go in and adjust this so that it recognizes the fact that because we are dealing with essentially a list of symbols here, these are all going to become symbols by the read operator. It will convert this guy into a symbol. So the first thing we need to do is when we go into, what was it? I believe it's going to be in remove if. Yeah, if we, let me go to translate to expression. When we go into actually translate to expression, we're going to probably have to go in and change this so that it will leverage and convert this into an appropriate uh, value. Now, when we look at this expression here, a couple of things that we can do. One is we could go and make this more complicated, this form, this translate to expression. Or what we can actually do is, as one way of potentially trying to handle this, is to leverage our existing rules-based translator, which I'm expecting is kind of leverage what he's suggesting. This hopefully does not overcorrect things. And we write a transform rule here, like in one of these, to have to go in and deal with the actual expression itself. So, um, so one approach is say we can adjust the y star example here to make this to being a float y and see what might happen. So we take this and only deal with floats if we need to. Now, granted, this is an overcorrection because if this operation is not um, a float operation, then we're always dealing with floating points. So I'll show you how we might be able to adjust this in this rules by adding an additional extension into the rule-based translator, because this we do have the ability to use Lisp code inside this rule-based translator too as well. But let's try this example and see what we can go. All right. So let's do this. So we've changed the rules translator. Let's go back. Let's go rerun this guy since we already have it. And let's see how our equations deal with it. No. So we need to actually go in and parse this and say symbol name y. Now, the reason why I'm doing symbol name y is I'm extracting the string from the actual symbol that we grabbed from the list, and then I'm actually um, going to run parse float. Wait. I think I could just do. Let me see if I could do float on this guy. Hold on. Float. Yeah, 6.5. Let's try that like that. Is knight of type real? Okay, that's fine. How did I look this up? There is a way of actually extracting the float. Parse integer, parser. Hold on, what was the code that I was actually going to take a look at? Determine start. Let me see here. We could potentially write our own float value, but what would that do? Oh, got it. That's right. We could do it this way. We could just do, let me see this. Read from string. Okay. And let's see if this actually appropriately float read from string. I think will allow me to do this. Okay. Hold on. Okay. So this correctly does what we need. So what we need to do is we need to do read from string. There we go. Update. Go here. Do that. Come here. And let's see what our equations look like now. Oh crap. Okay. This is not what we need. So this is getting injected into the code directly. So the rules, that's right, the rules-based transfer is creating the expansion. In the expansion, what is this? Expansion of the abbreviation is where we do a sublist conversion. Okay, 1 second. So there is another way of doing this. Okay, update that so we get back what we had before. Make sure that all that's set. Okay, so we're now back to where we did. I undid a lot of things, but that's okay. In our sublist, we do translate pair. Okay, so var pair. So another option that we could do is we can actually go and parse it here, couldn't we? If it's a symbol, we could force it to read it from the string so it could give us a value if but if it's an actual symbol it does not matter. Got it. I think I have it. One way of doing this is to maybe do this. If number p read from string exp. We want maybe list read from string exp. So this will basically parse it and give us the return. Let's see if this works. What is the unreachable code? Conflicted with asserted type list. Oh, because this is one type of atom, isn't it? Okay, then we're gonna have to do it this way. Let me go and change this. Okay. If number p. So we're just moving it into a condition here because this is handling the separate case. Read from string symbol name of the expression. And run list read from. We'll do some refactoring once because I know I'm referencing the same thing twice here. So this isn't efficient, but this will work for the time being, or should work. So let's see if, what is it complaining about there? Oh, here. Delete unreachable code, symbol name expression. Okay, so we need to actually go and parse the effing expression. Into equations. If I don't do it here, then the only other option is when we're solving this. Let me go and write this. I'm not a big fan of doing this in the solver itself, but we're going to have to maybe do it here. Okay, so let's see, one unknown here. Okay, to learn about one unknown, I need to check and see what it does when it parses an expression. Print exp. Okay, now let's run this first. EQN. So this is okay. Now let's run map car on this. We need to convert that 6970 into a actual real number. Translate to expression. So it has to happen in translate to expression. Sorry, create list of equations. Create list of equations. Let me go and see how this is actually generated. Okay. Okay. So here we have this guy we need to get rid of. Okay. Let's go in. Go to, sorry, this. Clear this so we can start from the beginning. Okay. Okay, so this started with the list of list of so this is that, so we don't need that either. No, 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 no. That's not it. The float P stuff I think I added last time, so this should not be there. At least I think I did. I'll go here. Just 1 second here. This is that is gone. And if I do that, that's all it is. Okay, perfect. All right, so in the list of equations, let's create equations. There we go. Create list of equations. We grab the list of equations to start out with. Okay, so that's what translate to expression is returning to us. So it grabs the first expression and it calls, hold on 1 second, this might be easier for me to do. Let me do is format t tilde a tilde percent sign exp and then say parsing, just so now what I'm looking at has a little bit more metadata. Okay, let's go here, run this guy again. Okay, so this goes into the last case. We're appending the create list of equations of the first expression, which we return as an atom to the rest of them. So now we're parsing the rest of this here. What we have to do is grab the next set and then move to the next object. So we're going to the rest here. All right. Okay. So what's happening here is we have to do this more finer grain. So here, since the first of the expression is going to be an atom, it's an equal sign. We need to make sure that the rest of the expression that that is creating matches the yeah, I think I know what I have to do. We need to create we're going to have to create a function that actually takes in that expression and makes sure that all of the symbols inside of the list are not numbers. So one way to do this is create a function. Let's do this. Diff, and we'll call this, I guess, create equation on the expression, and we will return here the actual expression. create equation on the expression. Let's do it that way. Okay, so we now have this. We now have this. And just to make sure that everything works, we're going to first make this a no op, just so that okay. And what we'll do is oops, come here, clear. Okay, so now come here, do that. Let's look at our equations, and hopefully it didn't create equations and list of equations. No, it didn't. Perfect. So now what we have to do is we need to unless, let's do this, unless all actually, let's see, what's one way of doing this? We need to make sure that all of these are numbers. Let's see. That's not what I want. What we have to do is we need to make sure and see let's see what we could do here. Let's see if I could do a map car on symbol P given equals price 69.70. What does this give me? This gives you a nil. Hold on. Nil. So how do we parse this guy? Let me see if I can do this. Map car read. see if this works. Okay. And value is not of type stream. Okay. So that's because it is attempting to read. Read actually requires an actual stream. Read read byte, read sequence is probably what I need. Invalid arguments 1. Okay. Let me see what this does. Sequence. Oh, this is going to require us to get it from the actual stream. Never mind. This is not what I want. For those of you who are just joining us and wondering what I'm trying to do is I'm trying to convert the expression directly using the existing read functions, but it looks like I'm gonna have to probably parse this myself, which kind of sucks. I was hoping that I would be able to like leverage something from the existing code, but since this is an expression with a bunch of symbols on it, let's see. Actually, since I have Alexandria, let's see if Alexandria has anything. Oh, I don't have Alexandria loaded. I could use Alexandria for this. I'd rather not. Got it. Let's see if I can do this. When actually let's do this. If Adam and first expression, so we know that it starts with an expression, and we want also we don't want to say it's an unknown because it's technically not that it's unknown. It's that not all of them are symbols. Let's see if I could do this. Okay, let's see. Okay, we're going to try an experiment on the REPL. Lambda exp. What we're going to do is we will write the following thing. And add first exp. So that's double checking that we have an operator at the start of the equation. Okay. Let me do some pretty printing here. Okay. And what's the second one? And here we reduce what do we want to reduce? We want to reduce, okay, should actually be not. And map car symbol P on rest of AXP. Start is going to be true, of course. And wait, what am I saying? Start is true. Initial value is true. Come on. There you go. There's our lambda. So the first one, we're guaranteeing everything, and we're making sure that at least only one of the values are going to be true. Now, obviously, when we go and deal with multiple expressions, we need to reduce them too, so that there's only going to be one unknown. So when we add with multiple unknowns, like when we deal with it, but for now, this was what we're going to deal with. And let's say price, and let's do a simple one. This one should be easy enough. Let's see what happens. And the macro name and was found. Oh, crap. Okay, so we can't use and on in. I didn't realize that and was not a function. It's a macro. Let's do. Let's see if I can do lambda. Pretty sure this is. Hold on, actually, before I do that, I need to go and remind myself one thing. Reduce lambda. I think I have to do xy here. Yeah, so it could take two arguments. So I could do the same thing here. I could say lambda x, y, and x and y. This should do exactly what I expected. It's true. So this actually will work. So if I end up putting, say, here, a pound 69.5 like that, this should give us a false. There we go. So now we have our macro. Okay. Okay. So if it does we need to find the symbol, and it needs to be handled in both directions. So like if the first argument is not a number, or second argument, but I mean if this first argument is a number and the second argument is a variable, we should be able to handle both directions. Um, so for now, what we would have to do is we'd have to implement um, we'd have to implement the essentially the equivalent of translate pair on the bindings with the response, and then we'd have to convert that. So you see, if we recall that translate pair bindings, that's getting the rules from, no, it's this one actually grabs the bindings from the rule response objects themselves. But we'd have to do something equivalent where we actually replace the expression location with the new value. Um, so it's essentially it's going to be a find and replace. Um, since this is a list of symbols, we could do that. Um, so first, what we have to do is take the expression, and let's see if we could use find if number p. Oh, right. If lambda, there we go, exp. Well, let's call this sym. And what we do is we say that this is a number p from read from string. This is basically what I was showing earlier. Um, symbol name sim. So we're converting the symbol into a string, so grabbing its symbol name from the object, reading it in, parsing it, checking to see if it's a number. That's basically what we're doing here. Okay, so this is our math. And what is our sequence? Our sequence is going to be, let's say, equals price, and let's try 6.5. It doesn't matter. Some floating point number. Let's see what happens. And we find it. So what is so 1 second here. Okay. So this, I thought, describe find if. We need to see if find if actually returns multiple values. What does the return value look like? Derived type, I don't give a crap. What is the return positional keywords? Use a compiled function. Does it give me a positional? Let me see if I could do a multiple value bind of the index of this, because multiple value bind, and we're going to call this index and sim. And what we'll do is we will return format G symbol tilde a index tilde a tilde %, and we do sim and idx go, idx go, index symbol nil. Okay, so it looks like this is only returning a single value. Find if is only returning a single value. And what we need is this index of, ideally. So in this expression, let me see. Find all if, no. Okay. Let me see. Oh, right. So we can actually do that. So we'd use find if, like so. We grab it, but then if we do, sorry, or position of item in our sequence equals price 6.6, it'll tell us it's 2. So, okay, so we can use these two in combination, and if we end up, so to replace it, we have to grab, let's see if we can do this. Okay, so now that we know the position, we know the things, let's use let. Okay, we're going to write a let binding here. Let our expression be, and let's do this so that way we can do everything in here. So first, let our expression be this guy for our example. I'm showing you what essentially what we're going to end up writing in create equation, but just bear with me for a second here. And then what we'll do is we'll find the symbol. Now, granted, I could, since I know what the symbol is in this case, I could just simply say the symbol is that, but I am trying to show you kind of effectively what the generalization of what we need to do. Um, uh, Find if lambda sim what this is doing is what we saw earlier. Okay, run that on our expression. So we now have our symbol, and then we need the position that it's in. Okay. Which is just position of symbol in our expression. And we want its value too as well. So we just do this, and then just do read from string exp. Okay. Oops, not exp. Sim. Symbol name sim. Yeah. Okay, so we now have our expression. We know the index in the expression that contains the specific symbol we're going to replace, what's its position, and what its value is. Okay, so now what we'll do is we'll simply do a set f, if this all works, on the element in our expression at that particular position with our value. Okay, and we're going to return the expression. And what happens? We ended up getting what we expected, and you'll now see that on constant data, destructive function set ELT on constant data. Oh, right. It's because I made that like, let's see if I can make this like so. price is oh, right, sorry. Boom. Oh, that also should be on intern. This is the problem with writing it this way, because we need to actually quote all of our symbols. And now we get what we're expecting. Okay, so we're gonna have to write this code here. And again, remember, this is going to handle the majority of cases with one unknowns. When we have multiple unknowns with the systems of equations that we're going to try and solve, that's going to take a little bit more time. Just because we need to essentially massage the equation so that, but that I think is doable too as well. Um, so let's go ahead and do this, which is the let's star stuff that I wrote. Luckily, I keep forgetting that I could actually grab this like so. Yoink. Paste. Okay. So we do not need this because that's passed in as an argument. Um, this is a little probably going to be a little confusing for all of us. So let's do this. Okay. Position, symbol, expression, and the value of the symbol. Let's see if okay. So if this all works, if we call this again unsigned byte 44 to find equals marked. Ah, got it. So the next problem is the fact that if there aren't any here, we're assuming in this one that there contains a symbol here with the number. But if there aren't any here, this is going to be nil. A symbol is going to be nil here. So what we need to do is we need to actually do this into two left forms, unfortunately, which is not a big deal. I just got to do this, and then this is going to be when sim k, and then we need to slurp this CZP, slurp the next one, and then the next one. Okay. else okay, then what we need to do is we need to go here. Oh crap, that's not what I'm going to do. Do here, go that, here, CPWR, CPSF, let, and CPWR, CPSF. This is slurping all this stuff. Now, for folks who are wondering these are just some of my special macros that I've written for allowing me to use smart parens directly. This isn't part of do Emacs. Um, okay, let me go and pull this guy here and then do some indentation. All right, and exp. Okay, and then what we have to do is this guy needs to change to being here. There we go. EQ and S. Let's see what our equations are. 65 marked. All right. I think we got everything. So let's go ahead and try and run this guy the way we expect it. Where is student? Let's do student on our words. Let's see what happens. And we have our final price. So to review, what we did is we're leveraging a lot of facilities that are available to us to convert Lisp objects directly. Okay, notice a lot of this is just accessing the standard library, the the not C++, the Common Lisp standard library functions. And we had to kind of write some adjustments to essentially read in the Lisp images. Because we are leveraging Lisp symbols, and Lisp symbols themselves are objects that contain the symbol name. What we could do is we could extract the symbol name, grab the string from it, and then leverage, again, the normal Lisp string manipulation utilities to go in and grab the numbers that we need for this case. Now, folks might be wondering why I use numbered versus float here. Ideally, it's true that I could just simply say float because integers are already being added. Um, but in cases where, for example, if you had, say, a comma or something like that, um, it this at least I think would do the appropriate thing of actually going and extracting the number from the actual string. Um, but this also is perfectly all right. So because number is the general predicate to see if it's an integer or a float, but since we are dealing with floats here specifically, this will also work, and you'll see that you'll get the same functions. Same answers. So we handled that. Let's go and look at one of the other ones that it was. Um, I think these other two might work the same, but we will see. Let's try. Uh, okay, let's try this one. So this is exercise 7.6b for folks who are following along. Okay, and I like writing out the equations like this just so that it's easier for us to, you know, leverage and manipulate them. Obviously, you could use let form if you really wanted to, but um, okay, let's call this 7.6b. And right, because of the fact that I am using Ch7, let's say this P6-B. This will work, right? Um, oh, wait, never mind. I didn't have a. I use a def parameter instead of a def var. So if I did this, this will work. So this will not work. Okay. Let's go and read the problem. The number of soldiers in the Russians have uh, is 1/2 the number of guns they have. Of soldiers the Russians have is 1/2 of the number of guns they have, right? Yes. Okay, and we need to make sure that we put that accordingly. The number of guns they have is 7,000. What is the number of soldiers? Okay. Let us create, let's see what student says up front when we do this. Is guns divided by 2 equals 7,000. What is soldiers? So we have an issue with the fact that they didn't realize that the number of guns is already provided. Um, Guns is actually 7,000. So how do we modify this? Um, is 1/2 the number of guns there. Okay, so maybe if I put a space here, like so, do that. Let's see. Yeah, there we go. That's just a parsing error. You can see very quickly that this is actually doing what we expect it to, using the basic thing, which is pretty cool. Um, It appropriately figured out the what. It extracted what it is based on the common patterns and so forth. Let's try another one that is a little outside of this kind of structural thing. Okay. Um, Here's one. 7.6.f. Exercise F. Okay. So parameter. Okay. What is, this is kind of something that's pretty typical to X for that. 4 plus 5. And we're going to make sure that we handle all the special characters here. Times 14 divided by 7. Which is 70 divided by 7. It's 10 plus 14. Okay. So we know that this here is basically, for folks who are looking, this needs to get converted into the following. 4 plus divided by, and let me see, if I do 2, 4, this is 1/2. Okay, so we do plus 4 divided by times 5, 14, 7, which is 14, as you can see here. What does student give us when we parse it this way? And we do student 7.6-f 14. See, pretty straightforward. It's handling most of the special characters here. What about something like this? This is a pretty interesting one. This is a, now this is not handling multiple inputs, so this may or may not work because we haven't actually handled this particular case yet or with systems of linear equations. But I don't think this is a proper system of linear equations. We'll see, because there is one unknown here and it looks like it's a triangular matrix, but we will look at that. This is exercise 7.6-G. Def parameter 7.6-G. Oops. Okay. X times B equals C plus D. Okay. That's equation 1. B times C equals X. Okay. X equals B plus B. B equals 5. And what we need is to find what is X, C, and D. All right. What is, so if we wrote this as is, okay, let's see what happens. Okay. do we need to write what? I don't think we do, but we sometimes get surprised. Okay, go. And you're able to see that we actually solved everything. Since b is 5, x is b plus b, which is 10, it is correct. And since 10, we know 5c equals 10, which means c equals 2. And then, so what is 5 times 10, which is 50? That's equal to 2 plus d. So what's 50 minus 2? 48. This is actually solving what we've expected it to solve. So this is all great. But what if we try to solve this? Okay, the time remaining, let's see if this actually works. Okay, def parameter, oops. We're going to go back a bit and we're going to solve this one, which is a harder problem, 7.1. Okay, let's take, this is a canonical example. Okay, let's say that we have the following two systems of equations. 100 equals overhead plus, I think, yeah, running times 40. Okay. And let's put, so that we know that this is an equation. And let's say overhead equals 10 times running. Okay. So like in this one, you could see this is a typical x plus y. You could think overhead is x, running is y, x equals 10 times y. And you could, most people just, substitute 10 times y into the for overhead, or 10 times running into overhead, and then you get, you know, 10 running plus 40 running, which is 50 running, and you can actually solve the equations. 50 running is just, means running equals 2, so overhead is 2, right? Sorry, 50 running means, yeah, running is 2, 10 times running means overhead is 20, right? But let's see what happens when we do this with student. And I'm going to leave this one because this requires us to actually go and massage student to actually handle systems of equations too as well. And the reason why this isn't working is because, as before, this goes back to create equation. This is what we've already started and we need to extend. This basically requires us to go through and once we have our systems of equations, okay, and we could see that these equations actually still correctly get created when we do, where is that? Let me just grab this guy here, and I will just replace this yoink here with 7.1. Okay, we run it. You can see that it's already giving us kind of the start of what we need to actually go and convert. Naturally, in this case, we need to go in and we need to change in the solver. Uh, we instead of one unknown, if there's a way to convert this to actually handle substitution methods that we learned in kind of high school algebra, this will then allows us to, like, solve the problems. And the way we would do that is instead of one unknown, which will be our predicate to solve something, we have to change how what the unknown means. Like, can we use the unknown expression to be substituted into something else to reduce the number of unknowns that need to be handled. And then we have to also keep track of that when we're doing this. But that's going to take a little longer than we have time for. So I will end today's stream at this. Thank you all for joining. Um, just to give you a couple of announcements before I let you all go. We will be off the next 2 weeks, um, and we will reconvene on the week of the 26th. I do know that given some of these times on the weekends, there have been some requests to actually move CL study group into earlier in the week. I am looking into doing that. Stay tuned for those of you who are um, members of our meetup for more details regarding that. Additionally, for folks who are our avid YouTube viewers and anybody who likes our content on YouTube, please like and subscribe to Atlanta Functional Programming for more content, not just on Lisp, because Atlanta Functional Programming does do various other topics too as well. Although we are the home of the Common Lisp Study Group too. Um, we are also in need of talks for folks who are in the Atlanta area, both in person and for those of you who are outside Atlanta, if you're willing to actually provide an online talk, drop me a line. I'm available on Slack and Discord, and I will get you scheduled. I'm Bugram on Functional Programming Slack, as well as the Atlanta's Slack workspace Tech 404, and I squat as Bugram in the Lisp Discord server too. So with that, I hope you guys enjoy the rest of your Saturday. Thank you for joining us. I'll see you on the 26th. Thank you.